Hello everyone and welcome to our talk today about Work Package 5 within the context of 6G-DISAC project. My name is Ghassan Zafzouf and I'm lead research engineer at Bosch Research in Hildesheim, Germany. The title of our work package today is Evaluation through Proof of Concepts and Demonstrators. And as the title suggests here, this work package focuses on bringing the concepts and the theoretical results that have been developed throughout different other work packages in the same project to practical reality. And to guide our discussion today, we have two major parts. The first one will tackle the different basics of this work package, things like the key figures, the key objectives, how the interaction with other work packages work, and what are the achievements that have been reached throughout this last year of the work package. In the second part, however, we'll be presenting the different results ranging from the foundations of this work package to presenting and talking a little bit about the progress that have been done in the different demos for this project. Let's firstly start with the basics of the work package. Work Package 5 is a collaborative effort bringing together a strong consortium of 9 different institutions, either academic or from industry across Europe. We are working together on 2 major tasks in this work package. In the first task, we are focusing on identifying and selecting the key components to be validated and integrated later on. When we say here components, this includes the hardware as well as the software. In the second task, it is broadly defined as building and developing the demonstrators that will showcase the DISAC framework. To this end, we have different deliverables. In the first year of the project, we have already successfully published one deliverable, which is D5.1, that you can find at the following website. Our key objectives in Work Package 5 are twofold. We have, firstly, work package level objectives, as well as more broadly defined project level objectives. In the work package level objectives, we have 4 major goals which range from defining the actual configurations that we are going to test, the scenarios that we are going to implement, throughout the implementation of the different algorithms, techniques, and protocols that are being developed and have been developed in other work packages, such as Work Package 3 and 4. On a project level, it touches all of the objectives of the project. However, there's one prominent object tightly related to this work package and specific to it, namely developing and validating an architecture of the 6G-DISAC framework for some selected scenarios of interest. These objectives don't indeed exist in isolation. In fact, Work Package 5 is the central hub of the 6G-DISAC project by taking input from different other work packages, namely Work Package 2, by taking the defined use cases where the metrics have been set and where the architecture is being developed as input. Then the methods and the protocols and the different physical layer signal processing algorithms are taken as an input from Work Package 3 and Work Package 4. In WP5, these different algorithms and techniques are being implemented and tested in real-life scenarios to be refined and fed back into the respective work packages for further improvement and further refinement. On top of that, we provide results for dissemination and industry exploitation as well as standardization in Work Package 6. So far, since its kickoff last year in January 2025, Work Package 5 has performed some considerable progress. As a matter of fact, we have defined and compiled the specifications of the different components that are expected to be part of the different demos. And this goes along the requirements that come from the software side, namely from the algorithms, from the techniques, which are being developed, as I mentioned previously, in WP2, WP3, and WP4. All of this work has been published in the deliverable D5.1, which can be found in the website, as I mentioned at the beginning of this talk. Then one important thing is defining the final demo or the umbrella demo, which takes as input different components and different aspects from all of the other demos that are being developed in WP5. This demo, which relates to the automotive industry, is the assisted parking, and we will be talking about that a bit later. One other important result that we have achieved in this year is the definition of an interface in order to ensure a functional inter-demo integration. The interfaces that we agreed upon are the object list interface, which is compliant with an ISO, namely ISO 23150, that we will be tackling in detail in a few moments, and the so-called collective perception messages, CPM, which are well known in the vehicular communication field, which allows, among other things, the communication between the infrastructure and the vehicle. On top of that, all of this work has been done in close interaction with the different work packages in this project, more specifically with WP3 and WP4 for taking the algorithms and protocols, and WP2 for adopting the architecture that is being developed there. Let us now delve deeper into the results and outcomes of the work package, starting with the overall picture of DISAC. In fact, the DISAC framework, which is again distributed intelligent sensing and communication, encapsulates different aspects ranging from communication aspects such as the semantic communication, the full duplex operation, the MIMO support, and among other things, to the sensing aspect, which includes aspects like monostatic, bistatic, and multistatic ISAC, as well as how to fuse, how to compute, and to store all of this data. So by its nature, DISAC has different facets, and in our work package, we have different demos, each focusing on a particular set of aspects within the framework of DISAC. Nonetheless, at the end, different components from these various demos will be fed into one umbrella demonstrator, which is demo number 5, and that we call here the assisted parking demo. Before talking about each individual demo separately, let us first start with understanding a few aspects related to the foundations of this work package, starting with the ISO interface. The ISO interface is an international standard which defines and sets a common interface between the sensors, such as radar, LIDAR, camera, and among other things, and one fusion unit. As you can see here, the problem is that we have different sensors with different natures, meaning that, for instance, we get some point clouds from the radar. However, from the camera, we will be getting some frames. And roughly speaking, this ISO establishes 3 abstraction levels of data, ranging from the raw data to higher feature data, which is called here detections, up to the object lists, which is the highest level of data. In our work, we will be communicating object lists from different sensors to the fusion unit at the end of the day. We cannot overstate the relevance of this interface due to 3 major aspects. Firstly, we have to make sure that the fusion unit understands each of these different sensors, and this is what we call here the interoperability across the sensors and the suppliers. Moreover, as in the DISAC project, we will be adding different sensors, and we want to pave the road towards adding other additional sensors and additional components, for instance, like the reconfigurable intelligent surfaces, which are briefly called the RIS components, on top of other things. And therefore, it's important to ensure the scalability of our demonstrator that we have one standardized interface. Now let's delve deeper into each demo separately, starting with demo 1, namely the DISAC sounder-based setup. In this demonstrator, we are trying to collect high-fidelity real-life ISAC channel measurements. This work is of paramount importance because it allows us, at the end of the day, to derive suitable models for the ISAC channel, which is something relevant for standardization or analytical work. To this end, 4 setups have been defined. Namely, in setup 1A, we have 2 horn antennas, which are co-located. These horn antennas emulate a base station which is operating in monostatic mode. The monostatic mode means that the transmitter and the receiver are both nearby, physically nearby. Now we have a target which is between the base station and 2 virtual arrays. The virtual arrays here mimic the user equipment, or the UE as we call it briefly. Then in setup 1B, we are replacing one of the arrays, one of the virtual arrays, with another horn antenna, which allows some alternative directive illumination of the target, meaning that we are going to get another perspective or another reflection of the signal coming from the target. In 1.C, we are introducing a new component, namely a hybrid reconfigurable intelligent surface, a RIS component. This RIS component is operating in higher band. In fact, it's operating in FR2. In all of these setups, 1.A, B, and C, we are modeling a static UE by using the virtual arrays, which are obviously not moving. And to explore the dynamic case, meaning that the UE is in motion, we are supporting this by introducing a 4x4 MIMO channel sounder and using a rubidium clock, which enables a synchronization between the transmitter and receiver. The current status of this demonstration is that we have already some initial measurement results, which we are going to show in the following slide. Here we have a base station, which is modeled, as I mentioned previously, by the 2 horn antennas, a target which is moving on the following horizontal line. And then we have 2 UEs, UE1 and UE2. These measurements have been taken indoors, and the base station was operating in FR1 and FR3. As initial results, what we can see here in the following slide, in the 3 plots, what we are showing on the x-axis is the distance to the reflection. On the y-axis, we have the angle. Then in the left-hand side, what we show is the base station to base station link. And here, if we play the following video, we can obviously see as the target is moving, the reflection here is also moving accordingly. Then what we are seeing here static are the clutter or the static objects in the environment. The plot in the middle shows the base station to UE1 link, whereas the plot on the right-hand side shows the link between the base station and UE2. Now moving to demo 2, which is a 5G waveform testing platform, we're introducing a base station, as we can see it in the 5G generation, meaning that it is using 5G waveform to be transmitted in the environment, and then to listen to the reflections coming from the different objects that are present nearby. And this is done by a sniffer to better understand how ISAC using 5G waveform will behave, and therefore to better understand, by consequence, the performance that can be achieved when we do sensing using waveform for communication. As I previously mentioned, we have in this base station a transmitter which is located at the top, and then below it by approximately 75 centimeters, we have what we call the sniffer or the receiver. This receiver listens to the reflections coming from the environment, and the signals received here are going to be transmitted over the cable to an SPU. The SPU, or the Sensing Processing Unit, is a chain of radar processing operations ending with a Kalman tracking block. Now the base station is operating in the FR2 band with a bandwidth of 200 megahertz. For this POC, we have also some initial measurements that have been taken, and we are showing a snapshot of the results in the following slide. What we see on the left-hand side is the scene that is being recorded, where we have 2 persons playing the role of 2 dynamic passive objects Passive here refers to the fact that they are not connected to the network. The base station that I've shown in the previous slide is located here within the blue rectangle. Then on the right-hand side, what we are showing is what we call the periodogram. The periodogram depicts the strength of the reflected signals to the POC, where on the x-axis we have the relative speed between the object and the base station, and the y-axis depicts the range between the base station and the respective reflection. We can see that we have a person which is moving away from the base station and another moving towards it. And in the respective fields here, the blue and the red rectangle, we can obviously see two objects as well, two reflections with changing ranges. After several experiments and several studies, it turns out that indeed the system is quite accurate in a line-of-sight environment with approximately 10 meters coverage. Moving to Demo 3, where we tackle the realm of semantic communication, several partners in the project are working on this topic. In fact, they are developing a test bed, including a USRP, which generates what we call semantic waveform. The semantic waveform that is being explored in this demonstrator is the OSSD, which stands for Orthogonal Semantic Sequence Division Multiplexing. The basic idea in this futuristic concept is to go a bit beyond transmitting just bits, to extract the meaning from the message, which happens firstly in this instance using a Python code, and then map these meanings or this semantic to a particular codebook which is AI generated. The USRP sends first the generated waveform in the environment and then listens back to the reflections. The main purpose here is to study the resilience and robustness of this waveform, which have been theoretically and analytically studied also in simulations, now in a more real-life environment. Demo 4 brings us closer to the last use case, which is being investigated in the project, namely the assisted parking use case. Here the partners are developing methods and devices for ultrasound radio sensing. The basic idea in this demo is that a user has a unique ultrasound signal which is transmitted, let's say, when it arrives to the parking premises. The infrastructure listens to the signal transmitted by the user. In this instance, it is a unique signal. And then in step 2, it performs an identification, authentication, and also possibly calculation of other parameters such as the range, velocity, angle of arrival, and other aspects. And then it allows the user in the premises. Here what we are trying to do is an ultrasound radio sensing in the close range environment. And this is particularly important, for example, for user authentication, in our case, in the assisted parking. Talking about the assisted parking use case brings us to the last demo, which is Demo 5, and as we call it in the project, the umbrella demo. The reason for this name is that it is meant to encapsulate and include several components and several aspects from different work packages that have been developed in the project and different demos that we talked about previously. The basic idea in this demo is that when a user arrives to the parking slot, let's say after going through the authentication that I just presented in Demo 4, and it is allowed into the premises, is now to firstly send to the user, detect and send to the user what are possible parking slots that are suitable for that particular vehicle. Then, in a second instance, after defining the trajectory and going towards the identified detected parking slot, is to monitor the environment and see, for example, if a passive object comes by, let's say a cyclist, a pedestrian, or maybe an animal or an object. All of these passive objects, again, passive here means that they are not connected to the network, could be detected by the infrastructure using different sensors, ranging from radio-based sensors like ISAC or a radar to the cameras which are also implemented. Using this information, the human driver in a first instance will be able to safely navigate the environment with relative comfort to the detected parking slot. Our aim, however, is to move from this level 2 system, meaning that we send only information to the vehicle, to the case where the car is in control. That means the car receives information from the infrastructure, but then computes a trajectory and takes a decision, which brings us closer to a fully autonomous system. The picture in the bottom here shows the test track that we have in Hildesheim, Germany, where we have already sensors which are implemented and functional, such as the camera shown in the blue rectangles here, and the lidar, which could provide some ground truth information. However, we plan also to add other cameras in the indoor environment, as well as radar, and with cooperation with other partners, we are planning on having risk elements implemented to help with the radio-based detection. Thank you so much for your attention. It was a pleasure to present to you the results and the progress that we have made in Work Package 5 after 1 year of its kickoff. And before leaving you here, I would like to invite you to our website and to visit our social accounts given on the following slide. Many thanks and see you soon.